So blockchain and IoT are two things that we don't tend to put together. We're going to think about, are they something we can make happen, or are they just this kind of unlikely pairing of two buzzwords? Because let's put it this way, blockchain's a massive buzzword and IoT is a massive buzzword. Can we make them work together? Is it possible? So when we think of blockchain, we tend to think of, not power efficient. There was meant to be a picture of a big massive power station there, because what happens, well, blockchain uses an absolutely massive amount of energy. One Bitcoin transaction at the minute is using about the same amount of energy as a US household uses in an entire day. And that's one transaction. You can fit 100, 200 transactions into a block, and you get one of those every 10 minutes. So that's a lot of power that's getting used. In fact, I think the whole Bitcoin network at the moment is using about the same amount of power as Denmark. Yeah, oops. It used to actually be even worse. It was 1.5 times that, because previously people were mining on their general purpose computers. So they were mining their Bitcoins on their computers, burning power quite literally into heat. So I remember back when the Bitcoins first started, we used to joke about using your computer as a space heater in the office, and actually it was quite an efficient form of heating. And it still is if you can do it well. So that's not the point in Bitcoin. But I thought I'd start with that, to just pivot that into IoT, that we try and make things last for 10 years on a battery. Well, we're not going to be mining on IoT, so we can start with that. Mining is really wasteful. There's reasons for it. We can talk briefly about that. This is not a blockchain talk. There's no math, there's no equations, and there's no circuit diagrams. But it's important for transaction verification. We have to do mining. We just have to accept that it's there for good reason. But it's a bit of a balancing act, because we need this proof of work, but we're trying to do something with, we're trying to do something with blockchain, but we have to accept the proof of work's there. So let's not mine, okay? If we want to send something to blockchain from an IoT device, that's practical. We can do this. If we want to make a transaction, so in blockchain everything needs to be a transaction of some kind. We take an incoming unspent transaction if you want to work with Bitcoin, for example. So something we've received that we've not used already. We're then going to make some recipients and some amounts. We're going to sign that with the right key, and the right key is from the one that received the money. And then we broadcast it out to the network. If we're being IoT, then we probably don't want to broadcast. We probably want to forward it to a relay node that can then do the broadcasting for us, because having to stick around and broadcast to lots of people isn't very efficient in terms of power usage. So probably more sensible to forward to a relay. But we can make a transaction. That's fairly straightforward. It's a predictable power drain. It's predictable amount of time it's going to take. Nice and simple. If you are using Bitcoin, be very cautious of fees. The minimum that you'll really be paying for a Bitcoin transaction was about $5 or $6 recently per transaction. So Bitcoin that used to be useful to send someone $1, nah, you wouldn't want to do that. So you'd need to look at an alternative blockchain. In terms of use cases though, for this sort of thing, being able to transmit, why would we want to do this on an IoT device? Well, we can store audit logs. So if you've got logging or some kind of data on a device that you think, I want to store this somewhere where it can't be tampered with, it can only be appended, it can never be mutated, nobody can come along and clear them out, and it might work there. Or if you've got measurements, readings, data where perhaps people don't trust each other, you need to collate it together across multiple different places, then you could send those measurements or those readings to a blockchain. Obviously though, there are cost implications of doing this when it's $5 or $6 to use Bitcoin, so you'd have to probably use another type of chain. You could use it to initiate financial transactions or payments cryptocurrency. An example of this, I suppose, if you want to think about it, would be the Bitcoin ATMs, where people can effectively put cash in the machine or use a credit card payment and then receive Bitcoin. So that's initiating a transaction based upon that. And you can use it to timestamp information as well, because once you put something in the chain, everyone can kind of verify where it is in the chain, how far back it is, and then roughly when it was put in the chain. So there's the kind of 4 things we can do as an IoT device if we can just transmit into the blockchain. But if we want to receive, this might be more useful, I would argue, for IoT, but it's actually much harder to do. So if we were to receive things from blockchain, we could interact with smart contracts, smart property, so tokens and these sorts of things. We'd be able to, for example, have an IoT device like a door lock on an Airbnb, where somebody that rents the Airbnb engages in a smart contract, and that specifies a start and an end time of the rental, and during that period, the corresponding key would be able to operate the door lock. All sorts of things like that. You could do it for cars, pretty much anything. You could even do it for public transport if you wanted. You could use to see if payment services have been made, and if someone's paid for something, they can use it, and if they're not paid for it, then they can't. And you can use it to receive funds and check timestamps, see if things are there, things have happened, that sort of thing. So these could be quite useful for IoT devices, because I'm thinking, you could think about the different sorts of things that you could build and integrate with, a couple of actuators, some kind of sensors or things like that. Oops. So different sorts of things you could actuate and work with, and engage in the real world. But the problem that we face is power consumption. If we need to receive, we have to do quite a lot of things. So we need to check that a block has got that valid proof of work we talked about earlier. We need to make sure that someone did a lot of mundane, boring, repetitive, hard power consumption work, right? Just to make sure that block is real. Once we've done that, we have to verify that the transaction is actually in the block. Then we have to go through a Merkle tree of transactions. So what that means is there's loads of transactions in this fancy structure, and we have to parse through the structure and hash up each and every transaction. It gets quite boring and slow. Then we need to verify the input signature in each transaction. Verifying signatures is pretty slow. That's quite annoying as well. And if you've got multiple inputs to a transaction, then you have to verify for each input. So if you want to talk computer science, which I hate, it's ON. This is not ON in any way. This is kind of ON squared or cubed, or something that's not scalable. And people have even been talking about blocks. People could build transactions that actually would take potentially longer to verify than they would to mine. So this is something that's a real problem when you're running on a little ARM Cortex. Then we need to find if there's actually a transaction that is useful to us. So blockchain's been designed with the kind of assumption that we don't trust anybody, but who cares if we use loads and loads and loads of power? When you're on a little IoT device that's just woken up on its Cortex M1, that's a bit of a problem. And then finally, we advance the state record of our network. So check if anything happens. So did someone pay me? Did something happen that I need to know about? Did a smart contract get triggered? But blockchain doesn't convey state. So what I mean by that, to elaborate on that a bit more, is conveying state would be a bit like saying, right, Simon's got £100 and I've got £100. Okay, now Simon's got 120 and I've got 80. That would be conveying state information. What blockchain does is it conveys changes. So it says, I've given Simon £20. You have to know how much I had beforehand and how much he had beforehand in order to actually work that out and then work out how much everyone now has. We don't convey that in blockchain. We have to keep a record of it and then work with that later down the line. That is a huge problem for this. There are 54.2 million unspent transaction outputs in Bitcoin. What that means is there are 54.2 million transactions sat there that at any point in time someone can come and say, I'm going to spend that. And each of these has to have an address and a value. So the address is the one that can spend it and the value is how much is there. And if we think about that, that's a lot of memory. In fact, if you do the calculation, it's 25 bytes for an address, 8 bytes for an amount. Let's assume that everything's 100% efficient, which it's not, and we need 1.8 gigabytes of storage just to store the amount of money everyone has in Bitcoin. That's not going to happen on your ARM Cortex M1. So you don't want to try and do that on a Cortex or any type of little IoT device. You need to, effectively outsource this sort of processing to a server somewhere. And now that means you need to connect to the server and trust that the server is going to act in your interests. It's not really practical to hold 2 gig of unspent transactions and then parse every block that comes in. So every block in Bitcoin is 1 megabyte, and a block comes in every 10 minutes. So you've got 10 minutes to process the block, and you're going to receive, 1 megabyte every 10 minutes. So 6 megabytes every hour. You can do the calculations with that. So is there an easier way? Well, hopefully. If we can trust, the network in quotes, if we can trust someone else, if we can trust a server, then we can use simple payment verification. So this is a way that we can avoid downloading every single transaction and block and all those things and pulling it into our little IoT node. So your poor little Cortex M1 doesn't have to churn through these megabytes of data. We can just download the transactions that actually relate to us. And that would actually be quite nice, because we could say, right, I am this doorknob and I only need to care about things that affect me as a doorknob. There are privacy issues of this, but people have solved it. You can kind of tell the server in a nice, clever way that we'll not talk about because it's got disgusting math that I don't understand either. But it does all sorts of things, and it pulls the information in, and it can tell you only transactions that should affect you. And there'll be a few false positives, but it's okay. It's not a big deal. It lets you verify those transactions. The problem is we have to trust everyone else to verify. And in blockchain, there's no bank to go to and put your hand up and say, I got scammed if something goes wrong. So you have to be really certain about what's going to happen. And this is the kind of key message to take away from today in terms of blockchain if you are wanting to work with it in any sense of IoT. You can't trust other people. whether it's malice or whether it's just good intentions but bad execution. There was a time, this was 4th of July 2012 I think, and there was a bit of a mix-up in the blockchain, and transactions got approved in the blockchain that weren't valid because they didn't have the right signatures on them. But miners accepted them and put them in blocks. So if you were reading those blocks, you'd think they were valid unless you went and validated each and every single one. Any block with an invalid transaction is completely invalid. So any legitimate transactions in that block got reversed. If your transaction was in there, the one that gave you the money, you've got a problem. So in that case, they had to wait they were suggesting you waited for 6 hours during that incident before you ever accepted that any money had actually reached you. It's quite a long time if you're thinking about doing anything in real time with blockchain. As I said, people are lazy, miners are lazy, they'll do whatever makes them the most money. And in that case, they decided that they would make the most money if they just made blocks without checking them, because checking them was slow, so they didn't bother to check them. Yeah, no, that's not a good idea. So if it's too hard for miners, it's going to be a bit tough for our IoT device. So we don't want to try and verify everything. If we want to verify, if miners are checking the blocks, then confirmations will help. So when we've got a block, if someone else comes along and produces another block on top of our block, they're vouching for that block being valid. And if enough people do it, we can say, well, it's probably valid. But that means that we have to make sure that they're checking everything for us. You get a confirmation every 10 minutes. You'll not get it any sooner than that. What that means is we can't do anything in real time if we're going to wait for these confirmations. Real time is something that's quite nice because it's good for user experience. It's really good if someone can make a payment and get their beer here and now. Imagine trying to buy a beer with Bitcoin. When it takes 6 confirmations, 60 minutes to buy a beer, nobody's going to do it. If we're at risk of forks in the blockchain, no, like if something's going wrong, we could be talking 6 hours before you can really be confident that the transaction is actually going through. So you have to really make a call as to how much money is at stake. Is it £1 or is it £100,000? Because there's going to be a significant difference in how long you're willing to wait. So you need to balance this based on the risks. So you really need, if you are trying to integrate with the blockchain in any way, you need to be balancing risks in terms of how long are we going to wait, what are we actually going to check, are we going to talk directly to the blockchain, or are we going to have some trusted intermediary, are we going to build our own intermediary and then just talk straight to it, running on a server somewhere in the cloud, or are we going to use a third-party payment processor to do that for us? One final challenge to talk about in blockchain is which chain. You think about it, why would we have to ask which chain? Of course, it's the blockchain. Well, no. Actually, if you rely on someone else to read the blockchain, how can we make sure you're seeing the legitimate chain? Because anybody can make their own one and put their own data in it. So, this could be a problem. The right chain in blockchain is the longest chain that exists. So they all started at the same point back in history, and the right one is the one that's longest. And those are the rules. And everyone agrees to follow them. But if you're not seeing the full chain, you don't know that what you're seeing is up to date or even on the chain at all. Someone else can make their own one, and so long as they follow most of the rules, you'll not spot it. So you can trick someone to follow a valid but short chain. I'll show you a picture of that in a second, but nobody else is going to recognize these transactions took place. But your poor little IoT device sitting on its Cortex M1 that's only powering up every hour or two to solve things and check, it might get fooled into giving someone something that they shouldn't be getting access to. And that would let you double spend. So in double spend, effectively someone transfers the money to you in one transaction, but they keep that in a little secret chain that they're only going to show you. Meanwhile, in the real chain that they're going to show other people, what they do is they actually transfer the money back to themselves. And then if that one ever gets out, it will be rejected because it's already been spent. So you didn't get your money. So bit of a problem there. So in IoT, well, it's going to be difficult to get blockchain embedded fully in IoT. Blockchain is really a bit of a buzz. I'm still going to say it. Blockchain is a solution in dire need of a problem. If anyone finds a problem, then there's lots of people who'd like it written on the back of a postcard and sent to them. IoT devices realistically are going to need to trust some centralized entity, whether it's yours, whether it's someone else's, to actually do the difficult processing for them. Your IoT device, you really don't want that to use blockchain directly. You're going to have a lot of problems in doing so in terms of performance, in terms of the amount of CPU time, in terms of even the actual capabilities in that CPU you're going to need. You're going to need to run a full operating system. You're going to need to run a full Bitcoin client. It doesn't make sense if you want to do anything in power efficient. But that'll save you from being scammed, and that's really quite important because you don't want to end up with someone just scamming you and making you think you've got money when you've not. The worst case scenario is you've got an ATM machine, for example, and someone can come to the ATM and withdraw cash by transferring bitcoins to it. This could be quite fun, couldn't it? So here's the real blockchain, and here's the blockchain that server is showing you. So that server you thought you could trust, well, if you can't trust it, it's showing you these transactions here. They're never going to be in the real network. So you're getting shown that, oh dear. You get fooled into thinking that it's transferred the money to you, and actually the money's just been, it never got to you. But you think it did, so you've just given them cash and they've run. So it's easy to send data to put into the chain, but it's not easy to read it back and verify you get paid. If you can trust someone else to do it, then you're good. But what about power consumption? So I mentioned power consumption earlier on, but it's easy to be low power if you can only wake up to transmit. It's quite simple, because you can power everything down. Examples of this would be LoRa. Andrew will be talking about LoRa. Class A devices in LoRa, they only wake up to talk. Sigfox and other technology does basically the same thing. All the other low power wide area network things, they do the same sort of thing. They wake up, they talk, they shut down. And Wi-Fi, if you build it that way, can actually do that too, which is what we'll quickly look at here. Sometimes more is less. So when it comes to power consumption, we could use these ESP8266 modules. You can buy them online on eBay and places like that. They're really, really cheap and they're really good, but they're pretty high power drain. We're talking about 120 milliamps of current drain when you use them, 320 at peak. You can actually get up to about 320 actually running them as well sometimes. But 70 when you're scanning for network, which is not brilliant. But 40 when you're connected and idle. The manufacturer says 10 microamps, which would be pretty good when it's in deep sleep, but nah, it's not. I've never managed to get it to that, and it's really buggy and it crashes and it reboots and it just doesn't work at that level. So can we do better? Well, let's get an MSP430. Really cheap little chips from TI, pretty nice, but they last for years in a watch battery when they're in sleep mode. They've got loads of GPIO, loads of ports that we can plug into things, so we can use these to actually control the power pins on other chips. So you can add a real-time clock with a crystal, and you've got interrupts that are individually switchable on pins. So that's really good ways to save power if you're building a piece of equipment. So let's add that chip. I just took that one because it's the cheapest, smallest, lowest power one. We're talking microamps per megahertz if you're actually going to use it, but when it's asleep, you get 0.7 of a microamp. So that's pretty low power. That's going to last a long time. And then we use GPIO to wake and sleep with Wi-Fi module. That gives you really low power Wi-Fi. There's a graph there just to compare it. If you look at, that's the kind of normal, just use an ESP module. This is the one here for if you're going to use an MSP430 with it as well. So you can see that over different periods of transmission, this is how often it's transmitting. The less you transmit, so if you just need to wake up to send something, you can get some really pretty good power consumption here compared to just doing it normally. And the less you wait, the better. So low power blockchain, you only want to wake up when you need to transmit. Bloom filter sent to the server, then it can just tell you what you need to receive. Check for those every now and then. Ideally though, use some sensors to trigger your MSP430 to wake up the main chip to look. Because if you can tell, for example, that you only need to look at the blockchain when someone's trying to open the door, then you don't need to wake up and do anything at another time. It's even more power. Offload everything to microcontroller if you're taking sensor data, measurements, any sort of thing, telemetry, that sort of thing. Gather those, batch them up, store them in the MSP430, and when you need to send them, wake the chip up once and send it out. And that's pretty much you. But you need to trust the server's going to act in your interests though, so you might need to build it yourself or have a business relationship with the person that's doing it. So in conclusion, it's really easy to send to the blockchain. It's quite nice. You can get nice properties out of it. You can have logs, nobody can break, nobody can change, nobody can tamper with. But it might not be practical, especially if you consider transaction fees in the blockchain itself. You can read and validate things, but it's pretty complex. There's a lot of challenges in going to do so, and you're going to need to think about running a service that's going to do this in the cloud or in your own server somewhere, and then connect into that and make sure you're doing that securely so no one can pretend to be that server. Network connectivity can be tricky to get working at low power, but it is possible. We've done it. Get a second microcontroller and use that to control the chip enable pin on the Wi-Fi module. You'll get really good power consumption like that. But let's be careful, because blockchain is really cool technology, but people are often using it with actually, substantial amounts of money, real cash. So IoT is really bad at the moment about software updates and security. It's a pet hate of mine. We need security updates, we need software updates, but in blockchain, you really, 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 really need it, because there are things that happen, there are changes that happen, there's some that are coming soon, and you need to have timely software updates onto your IoT devices in order to keep yourself in sync with the blockchain. If you don't, then other people are going to be accepting transactions you reject, or vice versa. You'll get out of sync and you'll not have a clue what's going on, and people will be getting free service from you because they'll be putting transactions in that you accept and no one else does. There's a potential for 2 forks in the blockchain to come up in the next little while, I think before August or so SegWit and SegWit 2, and there's all sorts of politics and bickering between the two of them. But there's chances for fairly significant changes, and your device will need to follow these. And this is not a one-off. There's going to be more, so getting good updates out to devices is really important. So if you're going to do anything with blockchain or IoT, stay safe, be cautious, patch regularly. 2 big buzzwords. There is some nice potential there, but just be careful. Thanks.